Good afternoon, everyone. Today's note is going to be about exponential models. Okay, so this ties in to what we were talking about a little bit on Friday. We did the basic model, which is b to the x, and right at the end, we talked about model where you have a different initial value. So that's the starting point for this lesson, right? So a more general form for an exponential relation is f of x equals a times b to the power of x, where b is the growth or decay factor and a is the initial value. Okay, and then this next part, again, this is stuff that we talked about a bit on Friday. Okay, if your base is bigger than 1, okay, then your function is going to be exponential growth, right? The function will increase from left to right. Okay, if the base is between 0 and 1, okay, then we have exponential decay. Okay, so again, visually, what that kind of looks like, right? If it's exponential growth, right, the graph is going to look something like this, although maybe not so wiggly. There we go, better. Okay, and for decay, it's just going in the other direction, so something like that. Okay, there are a lot of different places where exponential growth and decay occurs. Okay, from some science applications, like population growth, okay, is one that's often modeled by a percent change. So that's an exponential relation. Okay, radioactive decay. So if you studied half-life at all in a chemistry or physics class, okay, that's an exponential relationship. Okay, it comes up in finance, so compound interest and annuities. When you did that in the grade 11 course, those were examples of exponential relationships as well. Okay, so in this note, okay, we're going to kind of review how to set these kind of functions up. Okay, so you should have some experience with this from the grade 11 course. Okay, so here's example 1. The number of a certain bacteria doubles every hour. Okay, the initial population in the culture of this bacteria is 36. Determine an exponential model for the number of bacteria after t hours and determine the number of bacteria after 8 hours have passed. Okay, so again, I'm going to write down our general form. Okay, you wouldn't have to write that down on a test or something, but right, again, our general form is y equals a b to the power of x, where a is our initial value and b is our growth or decay factor. So our initial value is 36. Okay, and it says it's doubling every hour. Okay, and say I want this in terms of t, so maybe I'll just do a little variable change here. I'm talking about a population, so let's call that p for population. Okay, and t is the time in hours. Okay, so there's our model. And now for how many bacteria after 8 hours. So we just go p equals 36 times 2 to the power of 8. Okay, and then it's just a matter of quickly running that through. So I have 9,216. Okay, so after 8 hours, that culture has grown to over 9,000 bacteria. Okay, we're going to go on to example 2. And again, just to whoever's running the video, okay, please make sure you pause it to make sure everyone has a chance to get down what's on the screen before we go to the next example. Okay, next thing we're going to talk about briefly is that how to convert percentages into growth and decay rates. Okay, because often you're given it as a percent growth, right, percent decrease, and you have to be able to change that into the value of b here. Okay, again, this really comes off the compound interest formula. So for example 2, right, an investment increases by 5% per year. What is the growth rate of this investment? Okay, again, if you think of what the compound interest formula looked like from last year, it was A equals P 1 plus I to the N. Okay, key thing here, I was your interest rate. It was per compounding period, but it's the same kind of idea here. So if it's increasing by 5%, okay, what I'm going to just do, okay, my B is going to equal 1 plus the 5%. Okay, so my B value would be 105. Okay, and again, the reason why that works is because when you multiply by that, okay, the 1 is the 100%, the existing amount, and the 0.5 or 0.05 is the extra 5% that it's going to increase. Okay, so similarly, okay, for example 3, the value of a certain kind of car depreciates by 12% per year. What is the decay rate? It's the exact same thing, except right, we don't have growth, we have decay. So to determine my value of B, I still start with the 1, 100%, but I'm losing 12%. So I'm going to subtract 12%, okay, and that leaves me with 88, or 0.88. Okay. Again, when you think about that, what that's kind of saying, right, losing 12% per year is the same as keeping 88% of its value per year. So you're multiplying by 88% over and over again in an exponential function. Okay, on to example 4. All right, a small city's population increases from 35,000 to 57,010 between 1980 and 1990. Okay, create an exponential model for the city's population growth and predict what the population was in 2015. Okay. So again, we're going to start with our base model here. So y equals a times b to the x. Okay. So what I'm missing here is my growth rate. So really I need to take a minute and figure out what b is. So I'm going to use the information I already have to determine the value of b. Okay, so I'm going to plug in what we already know. My initial population was 35,000. Okay, my end population, right, was 57,010. Okay, I don't know what my base is. Okay, x would be the time that's passed, right? So I don't really need to write that down. Okay, but we went between 1980 and 1990, so that means 10 years had passed since the initial population. So that's power 10. Okay, and now we'll do some rearranging and solve that for b. Okay, so divide both sides by the initial population. That's b to the power of 10. Okay, and then my last step would be solving for b would take the 10th root of that fraction. So 10th root of 5710 or 3500 is equal to b. Okay, so we'll run that through. I got 1.049997 and so on. Okay, so realistically, b is approximately equal to 1.05. Okay, so this is a little side note here. So therefore, the growth rate is 5% per year, right? Okay, because again, this part right here, that extra bit off the 1, that is my growth rate. So now that I have that, I can predict the population in 2015. So let's write out our equation again. Okay, I have y equals My initial value is 3,500. Okay, my growth rate is 1.05. Okay, and for the year 2015, right, how many years later is that than my initial population? So 2015, take away 1980, that's 35. Okay, so 35 years after 1980 is where we're going. Okay, and now it's just a matter of running that through your calculator. Okay, so if that growth maintained itself, we would be at 139,060 approximately. 61, I guess, if you round. Okay, it's 0.5, so we'll call it 61. Okay, so in 2015, if that growth had continued, the population would have been in the neighborhood of 193,000 people. Okay, we have one more, I think. Okay, what is the average annual rate of inflation if a loaf of bread costs $1.19 in 1991 and $2.95 in 2014? Okay, so again, this is similar to what happened in the last example. Okay, we're going to set up my model. Okay, I want to know about the rate of inflation, so that's tied to my value of B. So we follow the same steps. Okay, I'm going to plug in my loaf of bread. Okay, so my final value is $2.95. My initial value was $1.19. Okay, and now how many years are there between 1991 and 2014? Okay, that's 23 years. Okay, so now we're going to solve this for B. So I bring the 119 over. Okay, and then B by itself, we'll take the 23rd root of that fraction. And we have 1.04. Okay, so therefore, the average rate of inflation is about 4%. Okay, so that's your kind of refresher on setting up exponential models. For the homework, okay, it's actually not from the textbook. So you go to the website, there'll be a link up there for it. I'll show you what it looks like. Okay, this is what the handout looks like. Okay, so, and the questions that I want you to do are listed at the top of the page there. Okay, so that's the homework practice. It's coming from this handout. Okay, again, just go on your device or grab an iPad from the back, okay, and you can look that up and start hacking away at that. Okay, so thank you very much for watching, and I hope to see you tomorrow.